Okay, a video then on digital communications. We'll start off by going through what is pulse amplitude modulation. So pulse amplitude modulation, so we've got our analog signal, it's going through the sampling gate. Remember our sampling gate, the clock for that needs to be at twice the highest frequency. But in other words, we're going to sample at this point here. There we go. There we go. We're up and running. We're going to sample at that point there, and then we're going to sample at that point there. So what we need to do then is just to draw in what voltages we got at those points. So the voltage we got in at that point there was the size of the pulse, and it was like so. Size of the pulse there, just below the second line. So we got something like that, and then looking at this, 1, 2, 3, 3.5 up. So 1, 2, 3.5 up, and a pulse like so. So that's pulse amplitude modulation. Basically, it's just measuring the voltage at that point in time. Whereas then if we look at our pulse width and pulse position modulation, then we're going to vary our width to start with according to the pulse. Now these are all our signal is all positive, so therefore this is our original pulse train, so it's going to get wider than this. If we had any negative voltage, then it would get narrower than this. So if this is our maximum, then on pulse width modulation, then I'm going to go something, I could probably go something like this for my maximum. Okay, at this point in time I'm measuring that voltage there, at this point in time measuring that voltage there, and at this point in time measuring that voltage there. So this is where I need to be careful. So this is my next highest one down. So sorry about the opposite. Okay, so if I then go next highest one down, so therefore if I go to do it the next widest width, this one here is slightly lower voltage than this one here, so I shall go slightly narrower than that one, like so. And then this one is the lowest voltage, so then I'll make this one somewhere around about there. So they're all in proportion to each other. So that's pulse width modulation. The width varies according to the amplitude. Okay, so pulse position, this is our original pulse just here, so obviously this is a positive voltage, so this will then push our pulse in advance. So sorry about that, it's catching. Try putting that there. So let's put this one in advance. So if I put it in advance by this portion here, so that's my highest voltage. Okay, so therefore then if that's my highest voltage and I've gone 1, 2, 3 squares, and then this one here can be is my next highest, so I'm just going to pop it in there in proportion. So I'm doing everything in proportion. This one is, so if this one here was 2, and this one is slightly less, so it's not going to be 2, it's just going to be slightly less than 2, so I'll probably go somewhere around about here. And then this one then is my error, so I'm just going to do it just there like so. So the position in advance of positive voltage, the greater the positive voltage, then the further in advance you're going to go. Right, okay, so looking then on now into a question that's looking at a PCM system and effectively what the advantages of using and then using time division multiplexing within it. So we're told here that we've got a signal 20 Hz to 4 kHz. So we need to sample. So we've got a sample clock. We've got a sample gate clock that is going to be 2 times 4 kHz, which equals 8 kHz. And therefore we're going to be actually sampling, so 10 kHz is greater than 8 kHz, which it would meets the minimum Nyquist sampling criteria. Now, if we didn't sample at the correct frequency, then what's called alias frequencies would be created, okay, which is effectively an incorrect frequency on the output. So if I put 5 kHz in, it would result in a 3 kHz output. Okay, I'll let you worry about looking through the notes how we came up with that figure. The resolution of the system. Okay, well we're told that we've got a 10-bit system, and we've got an input voltage range of 5 volts. So our resolution then equals range divided by 2 to the n. So we've got 5 volts divided by 2 to the 10, which equals 4.88 millivolts. Calculate the number of separate audio that can be combined into this link. Okay. So I might do this slightly differently to other people. So we've got our output. It's going to be sampled at 10 kilohertz. So we're going to do 10 bits. It's going to be every 100 microseconds. So we're going to produce 10 bits every 100 microseconds. So we need to send the 10 bits out at a rate of, so you can see that our PISO clock is 1.45 megahertz. So 1.45 megahertz equals 869 nanoseconds. But we've got to then send the 10 bits out at that rate. So that's what our PISO clock is running at. So it's running at that, and it's going to go first bit, second bit, third bit, fourth bit. So therefore, if we then 689 nanoseconds times by 10 bits should tell us how many effectively, if we've got 100 microseconds, and we're going to, so that equals 6.89 times 10 to the minus 6. So therefore we can send out a channel in 6.89 times 10 to the minus 6 seconds. So how many of those can we fit in that 100 microseconds? So 100 microseconds divided by the 6.89 times 10 to the minus 6 equals 14.5. Well, we can't send out a half a channel, so it's going to be rounded down to 14 channels. Right, okay, let's draw our PCM receiver. So let's think about how we're going to draw this. So first of all, we've got a series of pulses coming in series, like so, but they won't be really nice like that, so we might want to tidy them up. So first of all, we're going to put that through a Schmitt trigger gate. Then we need to convert them from series to parallel. Okay, so that we can send them to our digital to analog converter. So our digital to analog converter, so our digital to analog converter there. So we've got multiple lines going to that. Now in order to shift them out, we're obviously going to need some sort of clock. Okay, like so. Once we've sent them out, so our output there from our digital analog converter looks, it's back into analog, but it's a bit blocky. So therefore, if we stick that then through a low pass filter, we'll round it off. And there is our block diagram for it. Okay. So serial in, parallel out. Let's draw what we've got. So first of all, we've got serial in going into the first flip-flop. Now we need to shuttle the bits in from one flip-flop to another till we get our outputs. And the thing to remember is that the most significant bit goes in first. So most significant bit there is there is the least significant bit. And therefore we've got, and then because we want it all to happen at the same time, we're going to connect the clocks all together so that each of the bits gets clocked through at the same time. So we get the first bit in, most significant bit in, goes to there, next clock pulse goes to there, next pulse goes to there. So let's see that in practice. Let's see that in practice. So this is time 0, okay, and that's some time later. So remember I said that most significant bit is going in first, and just looking at this, so it looks like our data is 10 10. That's our data going in. The reason why I'm doing that is because sometimes it's useful just to draw a little bit of a table. Okay, so we've got A, B, C, and D. Like so, and we've got 1, 2, 3, 4 clock pulses to see that data in. So first of all, our data is 1, then the next clock pulse will send a 0 through, then we'll send a 1, then we'll send a 0, and we're going to then finally feed a 0 back through at the end. So to start with, we've got at no clock pulses, we've got 0 in, and then what happens is that 1 will feed down to there, and then that feeds across, and we can already see that because first of all it's partly drawn in for us, and then that 1 will get transferred to there, and then that 0 will get transferred into here. Let me just line things back up again. Okay, and then that's shifted along, so that 1 goes to there, that 0 goes to there, and then that 1 comes in. And then finally that 1 goes to there, that 0 goes to there, that 1 goes to there, and that 0 goes in like so. Okay. So sometimes it helps to draw a table, because then I can then take what I've got in each of the columns and draw that in. So there's my first clock pulse, second clock pulse, third clock pulse, fourth clock pulse, and we do have a fifth clock pulse. So what's going to happen on that fifth clock pulse? Well, the 0 is going to come in, so we're going to have a 0, 1, so that 0 is going to be like so. So we just need to feed that through on the fifth clock pulse. So on the first clock pulse, that 1 is coming in. That's that 1 there. Okay. And then reading down the column, then on the next clock pulse there'll be a 0. So coming here on the next clock pulse, that'll be a 0. And then on the third clock pulse, I've got a 1. And then fourth clock pulse, I've got a 0, like so. So I'm just reading down the column. So spend time to save time. Column B, on the first clock pulse, I've got a 0. So first clock pulse, I've got a 0. It's then on the second clock pulse, then B goes to a 1. B goes to a 1. third clock pulse it goes to a 0, fourth clock it goes up to a 1, and then on the fifth clock pulse there B goes to a 0. So we end up with like that. C is the third clock pulse, it's going to go to a 1. So 1, 2, third clock pulse, it's going to go to a 1, and then come down like that, and then it's not, and then it's on the fifth clock pulse, it will go back to being high again, like so. D, it's the fourth clock pulse, it goes high, and then it goes low. So just here, it's going to go up, up like so, and then on down there like that. Quick check of to make sure everything's all lined up. So the table helped in making it possible to do that really quickly. If we then look at the parallel in serial out, so this would be in the transmitter side, after we've got the digital to analog, the analog to digital converter. So I'll just do a table here at the same thing, because 1, 2, 3, 4 clock pulses. We've got QA, QB, QC, and QD. Okay, so on the first, so what happens to start with on this is we've got our parallel input here. We get a load, and then once we get our load, then we can set or reset. The respective flip-flop would be set, so that information would be loaded in. So into flip-flop A, we're going to have 1, 1, 0, 1 loaded in. Okay, then on the first clock pulse, after that's been loaded in, that's effectively this information, because that's that QD, that's QD there, is on our output, so it's shuttling out. So therefore everything shuttles across 1, 1, 0, and then we've got, so that's on the first clock pulse. Second clock pulse, we've got that. On the third clock pulse, we've got our 1 there, like so. So let's draw what we've got from that. So first of all, reading down our columns. So QA is, beg your pardon, I'm going to reset there. So at that point in time, therefore that will go to a reset. Everything's going to be reset at that point in time. There we go. And then we do our load. So we're doing our load. So we got 1101 coming in. So when we do our load, where's that one there? So we're going to have a 1. 1. Okay, so I've just zoomed out so you can see what we've got there. So you can see here now we've done our load. We've got 1101 loaded in. Okay, and then on the first clock pulse, we should look at that. We've got a 0 waiting in. So and then after the first clock pulse, looking down, then this is going to go to a 0, because the 0 is going to come in. So we're going to have a zeros all the way down there to flush out our register. So effectively, we've only got that 1 there to start with. So on that first clock pulse there, then that is going to go low, and it's then going to stay low. Okay, looking down column B, so on the first clock pulse it will stay high because we've got a 1 there. So to that point there, and then come down. Yes, I should be using a ruler, but then looking at the diagram, we're going to have zeros there, so that's going to go along there like that. Column C, on the first clock pulse it will go to a 1, so on the first clock pulse it will go to a 1, and then it will remain at a 1 for that clock pulse and the next clock pulse. So therefore on the third clock pulse it will go to a 0 like so, and then on QD, on the first clock pulse it's going to go to a 0. Okay, on the second clock pulse it's going to go to a 1. Where's that second pulse? Just there. Oh, line slightly out there. So then we've got 2 clock pulses, 1, 2, and then on this 4th clock pulse there it's going to go to a 0. Hopefully that's in line. Oh, there, like so. And there's our final answer on that. Right, we're on the home straight now, looking at Schmitt triggers. So we've got, if that's our hysteresis loop for a Schmitt trigger, looking at it, we've got saturation points here at plus 10 volts and minus 10 volts. Switching thresholds, the upper threshold there is at 8 volts and the lower threshold there is at minus 2. I just inserted a quick sketch diagram so you can then see how would that look like if we applied it to this. Okay, so definitely know that our output is going to be we've got down here, we're past the minus 2 points, so we've got minus 10 volts out. Oh, there we go. So we're going to have minus 10 volts out. At our threshold is at 8 volts, so at this point in time here, our input rises past that 8 volts upper threshold, so therefore we get plus 10 volts out, and it's not until moving across this point here that it crosses the signal goes down and crosses the minus 2 volt point. Again, best practice, use a ruler. So therefore it will go negative, and going here, signal then goes above the 8 volt mark. Where's that at? Just there, is that line? Like so. Where's the minus 2 here? Somewhere there. So we end up with a redigitized signal there. We've got rid of any noise and interference using our Schmitt trigger gate. Okay. Here we go. Right, okay, so we're going to need to design this Schmitt trigger. So we've got a 2 volt reference. So it doesn't matter in this case if we've got a 2 volt reference, but I thought it'd be useful. So we've got so we've got 10 volts out, and we're going to go to minus 10 volts. So I'm going to use the lower threshold, because that's the point in time that the output will go from 10 volts to minus 10 volts. So my lower threshold is minus 2. So in terms of where current is, if I've got 10 volts out, current is going in that direction. So I haven't drawn on my circuit, so we're going to have a resistor there, we're going to have a feedback resistor like so, and that point is going to be connected to there. I'm going to call that R1, I'm going to call that R2. Now, the ratio of the two resistors is going to equal to the ratio of the voltages across the two resistors. So if I've got 10 volts here on the output, when it's looking to switch from trip point, strip over to the opposite saturation point, the two input voltages should be the same. So I should have 2 volts there. So therefore, the voltage across R1, 10 volts here, minus the 2 volts that I've got just here. Then with the current going in this direction, so over the lower resistor I've got 2 volts minus the minus 2 volts that I've got on V in as my lowest saturation volt. So therefore I've got 8 over 4. 8 over 4 is equal to R1 and R2, so I can let R1 equal 8K, R2 equal 4K, or variations on that as you see fit. Okay. Right. So here we have another question in itself. So looking at the PCM system. So if we've got a sampling frequency at 12 kilohertz, then just obvious reminder, the maximum highest frequency we could have there was 6 kilohertz. So we need to send all 10 bits. There's got to be sent out every sample. So therefore 12 kilohertz is our sampling rate times by the 10 bits that we've got to send out, so therefore our SIPO clock is 120 kilohertz. Right. So this is, remember, so this is a digital analog converter. So therefore we've got 2 to the 10 number of levels, okay, which equals 1024. But there's only 1023 above 0, okay? 1023 above 0. So therefore, in working out what our highest voltage is, we've got 1023 levels above 0 times by our resolution, which is 3 millivolts resolution. Resolution equals 3.069 volts. That's the maximum voltage we could put into our digital analog converter. Right, and onto the home straight. We're looking to do some more design work. Now we only had to do one resistor calculation, but if we're looking to calculate our trip points, then if the voltage ref is not 0 volts, then we're going to have to do this calculation twice. If the ref is 0 volts, then it's symmetrical, so we only have to do one calculation. So V out, it says it just here. So V out is 9 volts going to minus 9 volts again, so it's the lower threshold that I'm going to find out, and I always use that same method. So I know that the ratio of the two resistors is the same as the ratio of the voltages across R1 and R2. So we've got 47K over 10K is equal to, well, I've got 9 volts on the output here. I'm going to have 2 volts just here. Just remind ourselves, I didn't draw it in, that current is going in that way, so that's the way it helped me to do my numbers, over 2 volts minus V in. Okay, so doing a little bit of tidying up, I've got 4.7 is equal to 7 over 2 minus V in. Little bit more tidying up, so 7 over 47 would equal 2 minus V in. So if I just leave minus V in there to start with, and then bringing the 2 to this side, so then need to subtract the 2 from it, gives me V in is equal to minus 510 millivolts. But it is a minus sign there, so therefore get rid of that minus sign. So therefore my lower trip point is going to be 510 millivolts. Right, and I've got to do exactly the same thing again for my V out is 9 volts going to plus 9 volts, so I'm looking for my upper trip point. Okay, my current, if my output is 9 volts, let's just look at this. If my output is 9 volts, there's 2 volts there, so so positive, negative, so current is going, so current would be going that way this time. So same ratio of the two resistors, 47k over 10k, so 4.7 is equal to the ratio of the two voltages. So this time I've got 2 volts reference minus the minus 9 volts that I've got on the output over, again looking at the arrow, my voltage in minus the 2 volts. A little bit of tidying up, 4.7 equals 11 over V in minus 2, showing all my workings. So 11 over 4.7 plus 2 is equal to V in, which equals 4.3 volts. And I think that is as done.